Most of the time, people, traditional form of linear mathematics is just a list of exercise, and then after you've done maybe 100 exercises, you get the concepts. But problem nowadays, our students don't do exercise list anymore. Because, my point of view, what's the best contribution for Mathematica done by computer is Wolfram mobile. Wolfram mobile, if you give I did this test, if you give me a list of exercise, a classical list of exercise, a steward book of calculus, in maybe I can solve 10 exercises in less than 10 minutes. Just use Wolfram. So that people don't understand concepts anymore doing exercise as a learning test. I don't know, I myself, it was that way. So what's the challenge you have, you see? The challenge is, okay, let's do the inverse problem. See? Computer math bad, that's cornered conference, a lot of people here in Wolfram. What's the path to using Mathematica for linear and so on? So it's do the opposite side, you see. Now what can compute can be used as teaching tools. What way you can put the concept inside the minds, that's a difficult, you see. People, they can have able to do calculus, can use Wolfram Alpha, no problem. But which way they can, the problem is in the concepts. So what we try to do, our model is the following, okay. I have a lot of subjects, a lot of demonstration projects, but when we go to real profession, for real school, the problem is, do you have material or not? So I want to ask you here, do you have material done, contents or not? You say, there's too many stuff, too many things to do. It's unable to do that one. So our idea is, okay, you are only to use what is in the NCTM. National Council of Teachers of Mathematics. They establish what is the main curriculum for America. When you look for PISA on other tests, okay, they have this, what the curriculum, the standard curriculums, standard focal points. Any problems you pick up, your choice is from this page. Or located in Brazil, that's where we have a huge program for graduate teaching, that's Prof. Math. That's around 1,500 mathematical teachers doing graduate recycle, and what they are doing. Okay, another requirement for the choice of the subject, you see, our subject must have a clear assumption of hypothesis violation. That's the problem. The students nowadays, they are mechanical. They do everything mechanical. They don't pay attention to the hypothesis. Let's return to hypothesis. What are you doing? That's the hypothesis, because we're trying to, what are the concepts in the brain? That's the question. See? Another thing is try to do, mathematics is great, okay, because they can do symbolic computation. And when they have errors, they warn us. Sometimes they don't have interrupt dynamic running. By the way, you can see here, CDF is better than Mathematica notebook. CDF is better. Because the machine in CDF, they don't stop to run the dynamic. CDF is better. Well, okay, let's see our problems here. Mathematical concepts in key focus of learning. Okay, let's see some examples. When you start this subject, it starts is the following way. You try to have a lot of demonstration examples. What I try to do is, you don't need to do example by example. Start from scratch every time. Let's have a toolbox. From this toolbox, the teacher can take the toolbox into teaching any concept to see. Try to study the limit of function, in the sense of the Cauchy. Given epsilon, I have a delta. They say epsilon delta, but it's Cauchy sense. And I developed this project. This is the first one. Okay, I show it's a function, but it can be any kind of function that maybe a function continuous or not continuous, don't care about what. If I have an epsilon, I can find a delta. Delta epsilon is smaller, delta is smaller, of course. All points are inside the function. Okay, is for nx. If when x go in critical points, like there is a clear non-continuous function in x equal 1, what happened? That's the problem. Deltas become more and more difficult. We are working and deltas become more and more difficult. Delta 0.03, and we go with a same epsilon, the box here, I can go. Each time, delta is less. What happens exactly when, what you guess, what will happen when exactly 1? Normally, I'll say, symbolic computation, normally there is an overflow here because I'm divided by 0. What is the warning of Wolfram said? That's indeterminate. That's great. That's what I'm looking for. Now I know what a continuous function is. There is a clear difference. It's because I'm unable to breathe the box around x equal 1. So since we start this problem, it continues to bring in mind some important points. See, first of all, limit is not a point, it's not a number. Limit is a process. You're doing by box, smaller. Limit is a process. Second point, I did a lot of exercise of limit in my life, lot of them. But I never realized that this program helped me understand mathematical concepts. I never realized that this problem proposed by Cauchy, in the sense of epsilon delta, is an inverse problem. That's an inverse problem. Why is it an inverse problem? It's an inverse problem because, no epsilon, okay. It's an inverse problem. That's good because when I watch the code, what are you using? What function I am using? Inverse function. If I am using as I notice, oh, that's right. Because given epsilon, I have a delta. So the problem of continuity in deep is a problem of inverse function. So some new concept I have been thinking about it. Maybe for yours is usual common, but for me it was a very new problem. After I noticed, see, okay, when there is no continuity, what's the message of Wolfram Mathematica? Say, well, it's indeterminate. But of course, I have new challenges. Let's see what's the example of a function that's not continuous, but it's continuous, but there is no inverse. What happened in that situation? I not show the code for this function. That's in my page in CDF. That's my CDF page. I have some examples. Okay, let's this function. That's a classical function. Okay, there is no inverse. And try to solve the limits for x equals 0. Sure, when we are out from the x equals 0, no problem. But the problem, I can't solve the programming using inverse function anymore. Which way I must to attack this problem? I must solve the equation. I must solve the use solve an equation and try to inverse in the small piece, because in the range it's not inverse, but in small piece it's inverse. So open more concepts. Well, let's see another example. Tangent p by 2. When Wolfram say, what's tangent to p by 2? Complex infinite, that's right. What complex infinite is? Complex infinite is indeterminate, it's a complex phase. Oh, that's okay. Let's see a problem here. I can go down. Which way go down? What Wolfram say for mathematics say for arctangent of complex infinite? Indeterminate, that's okay. But what Wolfram say for arctangent is, let me see, infinite. Here. Delete. What's arctangent? What do you think that's the answer? Don't know what ought to be the answer? Arctangent infinite. I not see my rule here. Yeah. Okay. What's tangent of infinite? P by 2. Wow, that's wrong. That's wrong. Maybe plus infinite. They say it's complex infinite. It's not. So arctangent P by 2 is not, because infinite is not a number. You are tracking infinite as a number. but maybe less p by 2 is the answer to, is acceptable to. So that's in the case of Wolfram. Maybe it uses this concept of limit. If I close the tangent p by 2 by right, oh yeah. Well, if I came tangent p by 2 by right, less infinite. So they say that arctangent of infinite is p by 2. So what are talking? So even some they say exact solution, even Wolfram alpha, we must take care. Pay attention for what we're talking about. In this case, if you have infinite by minus, okay, yes. Say p by 2 by right or by left, you have different solutions. Say you can say arctangent infinite is p by 2. So you and Professor Gadalla brought this problem. Professor Gadalla has a lot of exercise about tangent of p by 2. That's a very simple example. Let's see here. Okay, what happening? We are using. Okay, tangent of theta. Theta is k. K is integer. That's natural number. But what happening? Okay, you have the tangent on right. The sin is this segment, and the cosine is this segment. What happened when we go further? Okay, well, we are working in the p by 4. That's okay. When we go p by 8, that's okay. What happened with p by 2? What will happen p by 2? Let's go. When we go ahead and watch what's happening. B by 5. B by 5. P by 5 is, you know, tangent is negative. Okay. I don't like this. Okay. What will happen exactly is 4. Wow. Yeah. That's infinite expression found. That's if I have ZF, if I transfer this in ZF, I don't have to do now, must do now. Evaluation, a lot of people do this time. Stop dynamic, okay. So because if you watch here, what are you talking about? If you say that's a clear tangent, if there is a clear tangent, okay. Yep. Now I must evaluation again. Evaluation, dynamic update. Okay. 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 Here can read the problem. See, because we see, well, the parallels are going to infinite. So the concept infinite is not a number because here we can know in p by 2 that happens here. Okay, that's when k is integer. Okay, what happened if k is real number? It's not real. So that's the problem. What's the real? I don't like to show the code. When k is real, okay, real. So that's a very intense point to see. K now is real. What Mathematica said? Mathematica said, okay, when you go to growing, close to p by 2, tangent growing. I let float the range here, the I range. Okay, growing. Up. Oh. Does not overflow, not divided by 0. Because in this case, that's a good point to open. What's real is a machine is working. What machine is working with number? Is it a real number or a symbolic number? What kind of programmation are you doing here? In this case, you have that p by 2 is 10 to 16. Well, what does it mean? So that's, if you watch I watch here, if you can do, what's the machine precision? In fact, I look for the machine precision. The machine precision is 10 to 15. So when sometimes Mathematica works symbolic, you say, oh, that's overflow. I divide by 0. Don't stop the dynamical kernel. Or sometimes when I work for a real number, say, oh, that's a real number. Let's divide by smaller, up to the machine precision definition. So you are teaching for, let me see, for people who are doing programming or software programming, say, oh, what's machine precision? What's infinite for a computer? It's machine precision. So there is several opportunities to Mathematica show us to explore, to hook the concept, because the students don't think about that's the problem. Call attention for what the limits, what the contradictions, what the software can show us. Okay. Besides I go to this part of logarithm of b, I'd like to show a different example that we developed in our page. I really don't know if I was able to show time, but I have time to discuss a little bit. CDF. Okay, CDF is here. Okay, CDF. The problem is, well, that's amazing because I came to this problem using the mobile APIs from Wolfram algebra. Everyone teach by 3 points I have a circle, by 3 points I have a triangle, but nobody teaches that by 3 points I have a parabola. Never see this in high school, never. So when you are having more powerful tools like Mathematica, we can go inside deeper, different problems. When I was just funning with my Wolfram Mobile, I noticed that is in algebra, there is a problem, see, by 3 points I have a parabola, okay? What's the problem? Because you don't teach this one in high school. Why not in the curricula, these questions? Why not? The problem is, in fact, is a mixture of a lot of concepts, different concepts. You have, in fact, you must solve a kind of linear system. I must inverse a matrix. Nobody can do different points and try to invert different points of matrix. That's the point. But nowadays, you don't need to teaching how to invert matrix. How, maybe, I don't know if the concept of determinant is so critical. Maybe more concept like characteristic polynomial and so on is more critical. Because for Mathematica, you invert a matrix like that one is very easy. The algebraic, that's no problem. I just change the numbers, x1, x2, x3, no problem, okay? So it's very easy. All the problems is resumed to find this solution for this equation. This, how is the inverse of a matrix? We develop an example, like that one. We have 3 points, P1, P2, P3. And notice that the 3 points are in a parabola. The focus point is that one, the directrix is here. When you move the point P3, I can improve the locate and so on. What notes? See? Okay, it depends on the position of the P3, the parabola is there. The circle, you are mixing here a lot of concepts. First, linear matrix, inverse matrix, linear system, some kind of geometry, plane geometry. Because show that, oh, okay, this point P3, the focus, the same distance from the directrix. So everyone obey the rule of the parabola. Why people don't use to do that one? Why they don't have it? Because it's very hard to find limit. What happened, let me see here. CDF is great from my point of view, say, no problem. What happened, what, A equals 0. Oh, I love that. Okay. I love that one because in this case, okay, CDF don't block my computer, don't stop my computer. So they just say, well, that's a message say, don't stop. Why that one? Because in this case, what happened? A equals 0. I am violating a hypothesis. Which hypothesis? That the 3 points are non-linear. The matrix is non-singular. is matrix is singular, the determinant is 0, and so on. Okay, just a second. See, there's a question when Professor Gadalla has some example. When a very beautiful, they have more than 15 examples in when they move the basis of a logarithm. But I noticed with him, Professor, you did a trick, because here in my is unable to have 1 here. Why did you do that? I'm unable to have 1. It's okay. And your basis equals 0 to. Unable to have basis equals 0. To appear the problem, say they eliminate all sources of errors. I say no. I would like to see the errors. What Mathematica says for the errors? That's important key. That's he'll talk a little bit more about.
The way the logarithmic curve, as in all the books and all places defined, is that the base of the logarithm has to be bigger than 1. Okay, and well, we know that here is, if you look at, where's your cursor? Here. When ln x, you have two important, on ln x you have 2 important points, which is the e comma 1, that is ln x right there, and the 1 comma 0, all the logarithmic curves pass through that point, all right? And the log is this one, just to compare. Now, we know that we see the log when here, the base, that's the base of the logarithm. We're moving along, we can move all the way down. Now, if I go the opposite direction, what happens when the base becomes smaller and smaller, and maybe exactly 1? What happened? We have basically the equation, the straight line, vertical line, basically x equal 1 all the time. And that's not going to be a logarithmic curve anymore. And that is one of the main concepts. But what happens when the logarithm becomes, as the base becomes smaller, smaller, and then until it comes closer to the 0. When it comes close to 0, we have only one single point, 0, 1. That is one of the major concepts I needed to illustrate it. And I have to thank, actually, my students who asked me, many students ask me, what happens to the logarithm when the base becomes smaller than 1? What happens? What will be the curve look like? And that's when I decided to do this demonstration with Mathematica. See? With one bigger, otherwise it comes up, 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 and then we're going to switch gear. See, it's totally different ball game in here. And when it's exactly 1, you have just the vertical line, and we still have the point 1, 1. And I'll go further down. See, that is totally different ball game you're talking about, the inverse of that. Until I reach the 0, I got the point 0, 1. In summary, and actually I have to recognize and appreciate and thank to all the members of Wolfram Research, especially system support. I ran many times into many problems, and they have awesome people here. So very, very awesome people. I'm very pleased with what I have seen with the cooperation with. I have been so delighted to have Mathematica since 1990. We've been working on it, and very pleased with what I have been seeing. Thank you so much for attending.